Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillow. Let your body settle into wherever you are. There's no rush. We have all the time in the world. Where in the world are you watching from? A quiet bedroom as the day winds down? Perhaps a cozy corner where the night has already settled in? Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the most profound questions humans have ever asked. What sparked the Big Bang, if there was nothing? We'll journey to the very edge of existence itself, to that mysterious moment 13.8 billion years ago when everything began. We'll discover what scientists think happened in those first impossible fractions of a second, understand why the question itself might need rethinking, and contemplate what nothing really means when we're talking about the birth of absolutely everything. But don't worry. This isn't going to be an anxiety-inducing plunge into cosmic horror or existential dread. Instead, we'll move slowly and carefully through the most beautiful mystery science has ever encountered. We'll explore the evidence, meet the ideas, and sit with the profound strangeness of it all. By the end, I think you'll find a deep peace in not having all the answers, and maybe a new appreciation for the extraordinary universe we call home. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in, let your shoulders drop, take a slow breath, and let it out slowly. And let's begin our slow drift through the greatest mystery of all, the moment when nothing became everything. There's nowhere you need to be. Just listen and let the story unfold. Let your thoughts wander among the stars. Let's start with the question itself because it's worth sitting with for a moment. What sparked the Big Bang, if there was nothing? It's a question that feels almost impossible to ask properly, because every word we use brings assumptions with it. The word quote 1 suggests a trigger, a cause, something that made it happen. The word quote 2 suggests time already existed. The word quote 3 might be the trickiest of all, because true nothing, absolute nothing, is almost impossible for human minds to grasp. We think we understand nothing, an empty room, empty space. But those aren't nothing. They're still something, places where things could be. When we ask what came before the Big Bang, we're asking a question that might not actually make sense in the way we think it does. It's a bit like asking what's north of the North Pole. The question seems reasonable until you realise that north stops meaning anything once you've reached the northernmost point on Earth. There is no north of the North Pole, not because we don't know, but because the concept itself breaks down. Time, as we understand it, might work the same way with the Big Bang. Time itself, according to our best physics, began with the Big Bang. So asking what came before is like asking what's north of the North Pole. There might not be a quote 5 to ask about, but that doesn't satisfy us, does it? Our minds rebel against the idea. Everything we've ever experienced has a cause, a beginning, something that came before. We watch dominoes fall and we look for the finger that pushed the first one. We see a fire and we ask what lit the match. The idea that something, everything, the entire universe, could simply begin without a cause feels wrong at the deepest level. Scientists feel this too. They're human after all, with the same intuitions we all have. But they've learned to be comfortable with their intuitions being wrong, because the universe has surprised them so many times before. Quantum mechanics surprised them. Relativity surprised them. The expansion of the universe surprised them. Each time, reality turned out to be stranger and more wonderful than anyone imagined. So as we explore this question together, let's try to hold it lightly. Let's be willing to have our intuitions challenged. Let's be comfortable with the possibility that the answer might be, the question itself needs rethinking, or even, we don't know, and maybe can't know. There's a kind of peace in that. A recognition that the universe doesn't owe us easy answers. And perhaps most importantly, let's remember that not knowing doesn't diminish the wonder. If anything, the mystery makes it more beautiful. 13.8 billion years ago, something extraordinary happened. We call it the Big Bang, though that name is actually quite misleading. It wasn't big in the sense of being large, it was infinitely small, and it wasn't a bang in the sense of an explosion into empty space. It was the beginning of space itself. Let's try to picture it, though we should be honest that true picturing is impossible. At that first moment, which we call time zero, everything that exists now, every atom in your body, every star in the sky, every galaxy we can see through our most powerful telescopes, all of it was compressed into a point of infinite density and infinite temperature. Not a very small point. Not a point the size of an atom or even smaller. A true mathematical point. With literally zero size. This is where our everyday understanding starts to fail us. How can everything fit into nothing? How can something have zero size but infinite density? These questions point to the limits of our current understanding, hints that we're missing something fundamental about the nature of reality itself. From this impossible beginning, space itself began to expand. Not expanding into anything, there was nothing to expand into. Space itself was growing, creating more space as it went. Imagine the surface of the balloon being inflated, except there is no inside or outside of the balloon, just the surface itself stretching and growing. The temperature at this first moment was beyond anything we can really comprehend. Not just hot enough to melt metal or vaporize rock or turn matter into plasma. Hot enough that the fundamental forces of nature, the rules that govern how particles interact, were unified into a single force. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, all were one. The universe was perfectly symmetric, perfectly simple in a way it would never be again. This state lasted for an almost incomprehensibly brief time. In the first fraction of a second, things happened that would shape the entire future of the cosmos. The universe was changing so rapidly that more happened in the first second than has happened in some galaxies since. Temperatures were dropping not gradually but catastrophically, falling from infinity to merely billions of degrees in less time than it takes light to cross the width of an atom. We know this happened because we can see the echoes of it. The cosmic microwave background radiation, the afterglow of the Big Bang, still fills the universe. It's everywhere, coming from every direction, a faint whisper of those first moments. When old television showed static between channels, about 1% of that static was actually the Big Bang, ancient light from the birth of everything, still travelling through the cosmos. Scientists can take this radiation and work backwards, like watching a film in reverse, to figure out what the earlier universe must have been like. The further back they go, the hotter and denser everything becomes, until they reach a point where their equations start giving impossible answers, infinities where there should be finite numbers. That point, that wall beyond which our current physics cannot see, is the Big Bang itself. But that wall is not necessarily the beginning. It might just be the limit of our current understanding. To understand what might have sparked the Big Bang, we need to think carefully about nothing. Real nothing. Not the empty space between stars or the vacuum of space. True. Absolute nothing. When most people think of nothing, they picture empty space. The darkness between stars, perhaps, or the space in an empty room after all the air has been pumped out. But this isn't really nothing. Empty space, it turns out, is actually quite busy. It's filled with quantum fields, those fundamental fabric of reality that give rise to particles and forces. Even if you removed every particle, every photon, every atom, those fields would still be there, fluctuating and vibrating in their quantum way. In quantum mechanics, we've discovered something deeply strange about empty space. It's never truly empty. It seethes with what physicists call quantum fluctuations, pairs of particles popping into existence and annihilating each other so quickly that they almost don't count as existing at all. These are called virtual particles, and they're not just theoretical. We can measure their effects. They change the behaviour of atoms in ways we can detect and predict with extraordinary precision. This means that even the emptiest space we can imagine, space with literally nothing in it, isn't nothing. It has energy, it has structure, it has the potential for particles to exist. Philosophers sometimes call this quantum foam, a bubbling, fluctuating substrate that underlies reality itself. So when we ask what came before the Big Bang, if we imagine some void, some empty space waiting for something to happen, we're already imagining something rather than nothing. We're imagining space itself, and space is not nothing. True nothing, if such a thing is even possible, would be the absence of everything. No space, no time, no quantum fields, no laws of physics, no potential for anything to happen. It's almost impossible to conceive of because our minds work by constructing mental images, and you cannot construct an image of true nothing. Any image is something. Some philosophers argue that true nothing is actually impossible, that there must always be something rather than nothing because nothingness is inherently unstable or logically incoherent. Others suggest that nothing is the default state and that existence itself is the mystery requiring explanation. Lawrence Krauss, a theoretical physicist, wrote a book called Quote 9 says, in which he argues that empty space, even though it's not true philosophical nothing, is nothing enough for physics. The quantum properties of empty space, he suggests, are sufficient to explain how a universe could begin. Virtual particles become real particles, quantum fluctuations become cosmic inflation, and before you know it, you have a universe. But critics point out that this isn't really nothing. You still need the quantum fields, the laws of physics, the possibility of fluctuation. You're explaining how you get from something to something else, not from nothing to something. The deep mystery remains. Perhaps the question, why is there something rather than nothing, is the wrong question. Perhaps there has always been something, in some form, and the Big Bang was not a beginning but a transition, a change from one state to another. Or perhaps time itself is an illusion, and the concepts of before and after don't apply in the way we think they do. We should sit with this uncertainty for a moment. Let it settle. The not knowing is part of the wonder. Let's talk about what we do know, the things we can be fairly confident about. In the first second after the Big Bang, more happened than in some galaxies' entire lifetimes. The universe went through changes so dramatic and fundamental that the laws of physics themselves were different from one moment to the next. In the very first moment, what physicists call the Planck epoch, lasting from time 0 to about 10 to the negative 43 seconds, the four fundamental forces were unified: gravity, electromagnetism, a strong nuclear force that holds atomic nuclei together, and the weak nuclear force that governs certain kinds of radioactive decay, all were one single force. The universe was perfectly symmetric, governed by simple, elegant rules we don't yet fully understand. Our current physics cannot describe this epoch. General relativity, our theory of gravity and space-time, and quantum mechanics, our theory of the very small, give contradictory answers when we try to apply them to this moment. We need a theory of quantum gravity, a unified framework that merges these two great theories, and we don't have one yet. String theory, loop quantum gravity, and other approaches are trying to solve this puzzle, but we're not there yet. Then, around 10 to the negative 43 seconds, gravity separated from the other forces. It became distinct, the force that curves space-time and pulls massive objects together. The other three forces remained unified in what's called the grand unified force. The universe was still unimaginably hot, around 10 to the 32 degrees Kelvin, if those numbers even mean anything at that scale. By about 10 to the negative 36 seconds, something remarkable happened. The universe entered a period called cosmic inflation, where it expanded exponentially, doubling in size again and again in the tiniest fractions of a second. In a period lasting perhaps 10 to the negative 32 seconds, the universe grew from smaller than an atom to larger than a galaxy. This sounds impossible, like it violates the speed of light limit, but it doesn't. The speed of light limits how fast things can move through space, but there's no limit to how fast space itself can expand. Inflation solves several problems that had puzzled cosmologists. It explains why the universe looks the same in all directions, why it's so flat and uniform, why we don't see certain exotic particles called magnetic monopoles that should have been created in the early universe. Before inflation was proposed, these were deep mysteries. After inflation, they made sense. After inflation ended around 10 to the negative 32 seconds, the universe was still incredibly hot and dense, but now it was expanding at a more sedate pace. The strong nuclear force separated from the electroweak force. Quarks, the building blocks of protons and neutrons, began to exist as distinct particles. The universe was a soup of fundamental particles, too hot for anything complex to form. By about 1 microsecond, quarks were combining into protons and neutrons. By 1 second, the universe had cooled enough that these protons and neutrons could start to stick together, forming the first atomic nuclei, mostly hydrogen and helium, with traces of lithium and beryllium. The first matter, the first atoms, though it would still be hundreds of thousands of years before electrons could join with these nuclei to make actual atoms. All of this happened in 1 second. 1 single second that set the stage for everything that would follow. For stars and galaxies and planets and life. It's worth pausing to appreciate just how extraordinary that is. The cosmic microwave background radiation is one of the most important discoveries in all of science, and it's also one of the most beautiful. It's the oldest light in the universe, and it tells us more about the Big Bang than almost anything else we've found. For about 380,000 years after the Big Bang, the universe was opaque. It was so hot and dense that light couldn't travel freely. Photons would be emitted by a particle and almost immediately absorbed by another particle. It was like being inside a thick fog, where light scatters and bounces and never gets very far. The entire universe was a glowing plasma, uniformly bright in every direction. Then, as the universe expanded and cooled, it reached a critical temperature, about 3,000 degrees Kelvin. At this temperature, electrons could finally settle down and join with atomic nuclei to form neutral atoms. Mostly hydrogen, which is just 1 proton and 1 electron. This moment is called recombination, and it changed everything. Suddenly the fog cleared. Light could travel freely through space. The universe became transparent. Those photons that were released at the moment of recombination have been travelling through space ever since, and we can still detect them today. They've been stretched and cooled by the expansion of the universe, so instead of being visible light, they're now microwaves. But they're still here, coming from every direction in the sky, a perfect baby picture of the universe. In 1964, 2 scientists named Arno Penzias and Robert Wilson were trying to eliminate noise from a radio antenna they were using for astronomy. They kept detecting a persistent hiss that seemed to come from everywhere at once. They checked and rechecked their equipment. They even cleaned out pigeon droppings from the antenna, thinking that might be the source, but the hiss remained. What they had found, though they didn't know it yet, was the cosmic microwave background. Other scientists had predicted it should exist, but no one had detected it before. When Penzias and Wilson realised what they had found, it was immediately recognised as one of the most important discoveries in cosmology. It was direct evidence for the Big Bang, proof that the universe had been hot and dense and had cooled as it expanded. But the cosmic microwave background is even more remarkable than that. It's not perfectly uniform. There are tiny variations in temperature, about 1 part in 100,000. These tiny fluctuations correspond to slight variations in density in the early universe. Some regions were very slightly denser than others. Those tiny density variations were the seeds of everything we see today. The denser regions had slightly stronger gravity, so they attracted more matter. Over billions of years, those tiny overdensities grew, pulling in more and more matter, eventually forming the first stars, the first galaxies, and ultimately everything in the universe today. including us. We can map these fluctuations with extraordinary precision. Satellites like COBE, WMAP, and Planck have created detailed maps of the cosmic microwave background, showing these temperature variations across the entire sky. These maps are like fossils from the early universe, preserving information about what the cosmos was like just 380,000 years after the Big Bang. By studying these maps, scientists can learn about the composition of the universe, how fast it's expanding, how old it is, and what might have happened in those first moments. The cosmic microwave background has told us that the universe is 13.8 billion years old, that it's geometrically flat, that it's made mostly of dark matter and dark energy, rather than the ordinary matter we see around us. It's extraordinary that we can know these things. The light from the moment when the universe first became transparent is still travelling through space, and we can catch it and study it and learn the universe's secrets. Every time you see static on an old television screen, about 1% of those photons are from the Big Bang itself, ancient light from the dawn of time, still whispering its story to anyone who knows how to listen. Let's explore one of the strangest ideas in modern physics, the idea that the vacuum of space is not really empty, and that this might help explain how a universe could begin from nothing. In quantum mechanics, we've learned that there's a fundamental limit to how precisely we can know certain pairs of properties at the same time. This is Heisenberg's uncertainty principle, and it applies to many different pairs of quantities. One such pair is energy and time. The more precisely you try to measure the energy of a system at a particular moment, the less precisely you can know what that moment is. This has a strange consequence for empty space. For very brief periods of time, energy can appear out of nowhere, violating conservation of energy as long as it disappears again quickly enough. The briefer the time period, the more energy can appear. These temporary violations of energy conservation give rise to what physicists call vacuum fluctuations or quantum fluctuations. In empty space, particle-antiparticle pairs are constantly popping into existence and annihilating each other. An electron and a positron appear, exist for a fleeting moment, and then collide and vanish. A quark and an antiquark do the same. These are called virtual particles, and while they exist for such brief times that they're almost not real, they have measurable effects. One such effect is called the Casimir effect. If you place two metal plates very close together in a vacuum, the quantum fluctuations between the plates are slightly different from those outside the plates, because certain wavelengths don't fit in the narrow gap. This creates a tiny pressure that pushes the plates together. This force has been measured in laboratories. It's real. Empty space really does have this quantum activity. Another effect is the Lamb shift, a tiny difference in the energy levels of electrons in hydrogen atoms that can only be explained by vacuum fluctuations. Quantum electrodynamics, our theory of how light and matter interact, predicts this shift with extraordinary precision, and experiments confirm the prediction to many decimal places. So empty space is not empty. It's a seething foam of quantum activity. Particles and antiparticles appearing and disappearing, fields fluctuating and vibrating. And this raises an intriguing possibility. If particles can appear from nothing, even briefly, because of quantum fluctuations, could an entire universe appear the same way? Some physicists, like Lawrence Krauss and Alexander Vilenkin, have argued yes. A quantum fluctuation could, in principle, create not just a particle-antiparticle pair, but an entire universe. The universe would borrow energy from the vacuum, exist for some period of time, and then, according to quantum mechanics, it should eventually collapse and disappear. But something interesting happens if the universe inflates rapidly, as ours did during the inflation period. The expansion itself creates more space, more vacuum, and that vacuum has energy. This energy can pay back the borrowed energy from the initial fluctuation. The universe becomes self-sustaining, no longer needing to collapse and disappear. It becomes permanent. This is a remarkable idea. It suggests that our universe might have begun as a quantum fluctuation, a random bubble in the quantum foam that happened to inflate rapidly enough to become real and permanent. There was no trigger, no cause. It just happened, the way any quantum event just happens, governed only by probability. But there are problems with this idea. For one, it requires that the laws of quantum mechanics already exist, along with the vacuum with its quantum fields and its energy. So we haven't really explained where everything came from. We've just pushed the question back one level. Where did the laws of quantum mechanics come from? Where did the vacuum come from? Still, it's a starting point. It shows that the question of how something can come from nothing might not be as impossible as it first seems. In quantum mechanics, things happen without causes all the time. Particles decay randomly. Electrons jump between energy levels without passing through the space in between. Quantum mechanics is fundamentally probabilistic, not deterministic. Perhaps the universe itself is a quantum event, something that simply happened because the laws of physics allowed it to, with no deeper explanation needed. Cosmic inflation is one of the most important ideas in modern cosmology, and it might hold clues to what sparked the Big Bang. Let's explore what inflation is, why it was proposed, and what it might tell us about the ultimate beginning. In the 1970s and early 80s, cosmologists faced several puzzles about the universe. One was the horizon problem. When we look at the cosmic microwave background, we see that it has almost exactly the same temperature in every direction. The temperature varies by only about 1 part in 100,000. This means that the entire early universe must have been in thermal equilibrium at the same temperature everywhere. But according to standard Big Bang theory, different parts of the universe should never have been in contact with each other. They should never have had time to exchange heat and reach the same temperature. Imagine two regions of space on opposite sides of the observable universe. Light from one region wouldn't have had time to reach the other region in the age of the universe, so how could they have the same temperature? Another puzzle was the flatness problem. The universe appears to be geometrically flat, meaning that parallel lines stay parallel forever, and the angles in a triangle add up to exactly 180 degrees. But according to general relativity, the universe could be curved, either positively like a sphere or negatively like a saddle. For the universe to be as flat as we observe, the density of matter and energy in the early universe would have had to be fine-tuned to an extraordinary degree, accurate to many decimal places. This seemed like an unlikely coincidence. Alan Guth, in 1980, proposed a solution. What if, in the very early universe, there was a brief period of extremely rapid expansion? Not just expansion, but exponential expansion, where the size of the universe doubled again and again in tiny fractions of a second. This period, which Guth called inflation, would solve both problems elegantly. If the universe inflated rapidly, then regions that are now on opposite sides of the observable universe were once very close together, close enough to have been in thermal contact and reached the same temperature. Then inflation stretched them apart so far that light from one hasn't had time to reach the other. That solves the horizon problem. And if the universe inflated by a huge factor, any curvature it had would be stretched out and flattened, the way the surface of a balloon looks flatter and flatter as you inflate it to an enormous size. That solves the flatness problem. Inflation also solves the monopole problem. Certain grand unified theories of particle physics predict that magnetic monopoles, particles with only a north pole or only a south pole, should have been created in the early universe in vast numbers. But we've never observed a single one. Inflation explains this by diluting them. If monopoles were created before inflation, then inflation expanded space so much that they became incredibly rare, too rare to ever detect. But what caused inflation? The current theory is that inflation was driven by a quantum field called the inflaton field. In the very early universe, this field was in a high-energy state. As space expanded, the field tried to settle into its lowest energy state. But it couldn't do so instantaneously. While it was transitioning, it had a property that caused space to expand exponentially. Think of a ball rolling down a hill. The inflaton field is like that ball, starting at the top of the hill, high energy, and trying to get to the bottom, low energy. But the hill has a particular shape, relatively flat at the top, that causes the ball to roll slowly. While the field is rolling slowly down this flat region, space inflates exponentially. When the field finally reaches the bottom, inflation ends, and the field's energy gets converted into particles and radiation, heating up the universe. This is called reheating, and it marks the beginning of the standard Big Bang expansion. The beauty of inflation is that it makes specific predictions that we can test. It predicts that the tiny fluctuations in the cosmic microwave background should have a particular pattern, a particular spectrum of sizes and amplitudes. Observations from satellites like WMAP and Planck have confirmed these predictions with remarkable precision. The pattern we see in the cosmic microwave background matches what inflation predicts, but inflation raises its own questions. Where did the inflaton field come from? What determined the shape of its potential energy curve? And perhaps most intriguingly, inflation might not just have happened once. It might happen again and again, creating not just our universe but an infinite number of universes, a multiverse where inflation never truly ends. If inflation happened once, it might happen eternally, creating an infinite number of universes. This idea, called eternal inflation, is one of the most mind-bending concepts in modern cosmology. Let's explore it gently and see where it leads. Remember that inflation is driven by a quantum field, the inflaton field, rolling down a potential energy curve. In some regions of space, the field reaches the bottom and inflation ends, creating a universe like ours. But quantum mechanics tells us that fields fluctuate randomly. In some regions, these quantum fluctuations might push the field back up the hill before it reaches the bottom. When this happens, those regions continue to inflate while nearby regions stop inflating and become universes. The inflating regions expand so rapidly that they create more space, and in that new space the same process happens again. Some regions stop inflating and become universes, while others continue to inflate. This process repeats forever. The result is an infinite number of bubble universes, each one a separate cosmos with its own space and time and physical laws. Our universe is one such bubble. It formed when inflation ended in our region of space, but inflation never ended everywhere. Out beyond the edge of our observable universe, beyond the cosmic horizon that limits how far we can see, inflation might still be happening, creating new universes constantly. These bubble universes would be completely separate from each other. Light from another bubble universe could never reach us because the space between us is inflating faster than light can travel through it. Each bubble is its own isolated cosmos, expanding and evolving according to its own laws of physics. And here's where it gets even stranger. In different bubble universes, the laws of physics might be different. The constants of nature, things like the strength of gravity or the mass of the electron, might have different values. The number of dimensions of space might be different. The fundamental forces might be unified differently. This isn't just wild speculation. It comes from string theory and related ideas in theoretical physics. According to string theory, there are many different ways that extra dimensions can be compactified, curled up into tiny shapes too small to detect. Each different configuration gives rise to different effective laws of physics in the resulting universe. There might be 10 to the 500 power or more different possibilities, a landscape of potential universes. In eternal inflation, all of these possibilities might be realized somewhere. Every possible universe that can exist does exist, in some bubble somewhere in the eternally inflating multiverse. Our universe, with its particular laws and constants, is just one bubble among an infinity of others. This idea has profound implications for the question of what sparked the Big Bang. In eternal inflation, there was no spark for the multiverse as a whole. Inflation is eternal into the past as well as the future. There was no beginning, no first moment. The multiverse has always existed, always been inflating, always creating new bubble universes. Our particular universe did have a beginning. Inflation ended in our region of space 13.8 billion years ago, and that's our Big Bang. But that wasn't the ultimate beginning. It was just a local event, a transition from inflation to standard expansion in one small region of an eternally inflating multiverse. Of course, this raises new questions. Where did the eternally inflating multiverse come from? Why is there an inflaton field at all? What set up the laws of quantum mechanics and general relativity that govern inflation? We've pushed the question of ultimate origins back, but we haven't answered it. Some physicists are comfortable with this. Perhaps the multiverse is simply eternal, with no beginning and no deeper explanation. Others think we need to keep searching for a more fundamental theory, perhaps a theory of quantum gravity that explains why inflation happens at all, and we should acknowledge the controversy here. Not all physicists accept eternal inflation, or the multiverse. Some argue that these ideas are untestable and therefore not really science. If we can never observe other bubble universes, can we really claim they exist? Others argue that the mathematics is solid, and the predictions follow logically from well-tested theories, so we should take the multiverse seriously even if we can't directly observe it. There's a kind of humility in not knowing, in accepting that the ultimate answer might be beyond our reach. The universe is not obligated to make sense to us. It's not required to answer our questions, but we can still explore, still wonder, still marvel at the extraordinary ideas that physics has uncovered. Let's think about time itself, because understanding what time really is might help us understand what before the Big Bang could possibly mean. Time is something we all experience, something that seems so fundamental that we rarely question it. But modern physics has revealed that time is far stranger than our intuition suggests. In our everyday experience, time flows. Past moments are gone, future moments haven't happened yet, and we exist in the present, moving forward 1 second at a time. Time seems absolute, the same for everyone, an unchanging river that carries us all along together. But Einstein's theories of relativity showed that this intuitive picture is wrong. Time is not absolute. It's relative, flexible, dependent on motion and gravity. If you travel very fast relative to someone else, time actually passes more slowly for you than for them. If you're in a strong gravitational field, time passes more slowly than in a weak field. Astronauts on the International Space Station age very slightly more slowly than people on Earth, because they're moving fast and because they're in a slightly weaker gravitational field. Even more radically, relativity tells us that there's no objective present moment that everyone shares. What counts as quote 12 depends on how you're moving. Events that are simultaneous for one observer happen at different times, for another observer moving relative to the first. Time and space are woven together into a four-dimensional fabric called space-time, and different observers slice that fabric into space and time in different ways. This raises a deep question. Does time really flow, or is that just an illusion? Some physicists argue that the flow of time is not fundamental, that past, present and future all exist equally in the four-dimensional space-time described by relativity. From this perspective, sometimes called the block universe view, all of history, from the Big Bang to the far future, is laid out like a landscape that we travel through, but that doesn't itself change. If this view is correct, then asking what happened before the Big Bang might not make sense. Not because time began at the Big Bang, but because quote 13 and quote 14 are just directions in space-time, like north and south. You can go north until you reach the North Pole, and then north stops being meaningful. Similarly, you can go backward in time until you reach the Big Bang, and then backward stops being meaningful. But there's another possibility. Maybe time really did have a beginning. Maybe the Big Bang was the first moment of time with literally nothing before it. This doesn't mean there was a moment of time when nothing existed. and then suddenly the universe appeared. There was no such moment. Time itself began with the universe. Asking what came before time began is like asking what's north of the North Pole. St. Augustine back in the 4th century gave a similar answer to the question of what God was doing before creating the universe. His answer was that there was no before because God created time along with the universe. Time is part of creation, not something that exists independently. Modern cosmology, in a sense, has come to a similar conclusion, though for different reasons. Quantum mechanics adds another layer of strangeness. In quantum theory, the future is not determined. The universe is fundamentally probabilistic. When a radioactive atom decays, there's no cause for that particular moment of decay. It just happens randomly, governed only by probability. The future is not a fixed path, but a cloud of possibilities, with some outcomes more likely than others. This suggests that time might be even stranger than relativity indicates. Not only is it flexible and relative, but it might be fundamentally open. With the future not yet existing, even in the block universe sense, and if time can be strange in these ways, maybe it can be strange in other ways too, ways we haven't yet imagined. Some quantum gravity theories suggest that time itself might be emergent, not fundamental. At the deepest level, at the scale of the Planck length and Planck time, the concepts of space and time might not even apply. Time might be something that emerges only in the classical limit, when we're looking at scales much larger than the Planck scale. If time is emergent, then asking what came before the Big Bang is like asking what's inside an atom, in a world where atoms are the smallest possible things. The question assumes a finer structure that doesn't exist. Time might only exist in our universe, emerging from some more fundamental, timeless substrate, and quote 16 might be a meaningless phrase because there is no time there for quote 17 to apply to. We should let these ideas settle for a moment. Time, something so basic to our experience, might be an illusion, or an approximation, or an emergent phenomenon. The universe is teaching us that our intuitions, developed in the familiar world of everyday experience, can be deeply misleading when we venture into the extreme realms of the very fast, the very massive, or the very early universe. When physicists trace the history of the universe backward in time, their equations point to something called a singularity, a point where the density and temperature become infinite. Let's explore what this means, and why many physicists think it's a sign that we're missing something important. A singularity is a place where the mathematics breaks down, where the equations give infinite answers. In general relativity, Einstein's theory of gravity, if you trace the expansion of the universe backward, compressing everything into smaller and smaller volumes, you eventually reach a point where the volume becomes zero and the density becomes infinite. This is the Big Bang singularity. Similarly, at the centre of a black hole, general relativity predicts a singularity where matter is compressed to infinite density. These singularities are problems because infinity almost never appears in real physics. When your equations give you infinity as an answer, it usually means you're using the wrong equations or you're asking a question the equations can't answer. Physicists don't generally believe that singularities are real. They're more like warning signs that say, our theory stops working here. General relativity is a classical theory, meaning it doesn't include quantum mechanics, and we know that at very small scales and very high energies, quantum effects become important. So when we trace the universe back to sizes smaller than the Planck length, about 10 to the negative 35 meters, we should expect quantum effects to matter. The Planck scale is named after Max Planck, one of the founders of quantum mechanics. It represents the scale where quantum gravitational effects become important, where the quantum uncertainty in the position of particles becomes comparable to the curvature of space-time they create. At this scale, our current theories break down. General relativity and quantum mechanics give contradictory answers. What we need is a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics and can describe what happens at the Planck scale. Several candidates exist: string theory, loop quantum gravity, causal dynamical triangulations, and others, but we don't yet have a complete tested theory. These theories suggest different possibilities for what happens at the Big Bang singularity. In some versions of string theory, the singularity is replaced by a smooth transition. The universe might have bounced from a previous contracting phase to the current expanding phase, with no moment of infinite density. Time could extend infinitely into the past, with our Big Bang just one event in an eternal cycle of expansions and contractions. In loop quantum gravity, space is not continuous but made of discrete units, tiny loops of space-time. As you compress the universe, you can't make it smaller than these fundamental units. The universe reaches a maximum density, extraordinarily high but still finite, and then bounces. The Big Bang becomes the Big Bounce, a transition from a previous universe to our current one. In these scenarios, asking what came before the Big Bang has a clear answer. There was a previous phase of the universe, perhaps contracting rather than expanding, and the Big Bang marked the transition point where contraction turned to expansion. Time extends infinitely into the past, and the universe is eternal, though constantly changing. But these ideas are speculative. We don't have experimental evidence for any of them yet. The energies required to test quantum gravity directly are far beyond what any particle accelerator can achieve. The Planck energy is about 10 to the 19th billion electron volts, while the Large Hadron Collider, the most powerful accelerator we have, reaches only about 10 trillion electron volts. We're 17 orders of magnitude away from the energies we'd need. So physicists look for indirect evidence. They study the cosmic microwave background, looking for subtle patterns that might reveal quantum gravitational effects from the early universe. They look at gravitational waves, ripples in space-time created by colliding black holes and other violent events, hoping to find clues. They develop the mathematics of quantum gravity, looking for consistency and coherence, trusting that a beautiful, elegant theory is more likely to be true than an ugly ad hoc one. The Singularity Problem reminds us of the limits of our knowledge. We can trace the universe back to about 1 Planck time after the Big Bang, about 10 to the negative 43 seconds. Before that, we're in uncharted territory. We have ideas, hypotheses, mathematical frameworks, but not yet a definitive theory. And perhaps that's okay. Perhaps it's good to acknowledge the boundaries of our knowledge clearly, to be honest about what we know and what we don't. The universe has surprised us before. It will surprise us again. The answers we find might be stranger and more wonderful than anything we've imagined. There's a curious fact about our universe that might shed light on why it exists at all. The laws of physics and the values of the fundamental constants seem to be fine-tuned for life. If gravity was slightly stronger or weaker, if the mass of the electron was slightly different, if the strong nuclear force had a different strength, life as we know it couldn't exist. Let's explore what this means. Consider the strength of gravity. If gravity were much stronger, stars would burn through their fuel much faster, perhaps too fast for life to evolve on any planets orbiting them. If gravity were much weaker, stars might never form at all, or they might not generate the heavy elements needed for life through fusion. The range where gravity allows for long-lived stars and the creation of complex chemistry is relatively narrow. Or consider the strong nuclear force which holds atomic nuclei together. If it were slightly weaker, only hydrogen would be stable. No heavy elements would exist, no carbon for organic chemistry, no oxygen for water, no nitrogen, no phosphorus, nothing but the simplest atom. If the strong force was slightly stronger, protons would stick together too easily, and all the hydrogen in the early universe would have been converted to heavier elements, leaving no hydrogen for stars to burn or for water molecules. The cosmological constant, which determines the rate of cosmic acceleration, is another example. It's extraordinarily small but not quite zero. If it were much larger, the universe would have expanded so fast that galaxies could never have formed. If it were negative with a large magnitude, the universe would have recollapsed before any stars could form. The actual value seems to be in a very narrow range that allows for a long-lived universe with structure. This apparent fine-tuning has puzzled physicists and philosophers. One response is the Anthropic Principle, which comes in several versions. The weak Anthropic Principle simply observes that we should not be surprised to find ourselves in a universe that allows for our existence, because if the universe didn't allow for life, we wouldn't be here to observe it. It's a selection effect. We're biased observers. We can only exist in the small subset of possible universes that permit life. The strong Anthropic Principle goes further, suggesting that the universe must have properties that allow life to emerge, because observers are necessary for the universe to be real in some sense. This version ventures into philosophy and is more controversial among scientists. But if we accept the multiverse idea from eternal inflation, the Anthropic Principle becomes less mysterious. If there are countless bubble universes with different laws and constants, then we should expect to find ourselves in one of the universes that permits life, because those are the only ones we could possibly inhabit. It's like asking why you were born in a country that exists rather than one that doesn't. The answer is simply that you couldn't have been born in a country that doesn't exist. From this perspective, the fine-tuning is not evidence of design or purpose, but simply a selection effect. Most universes in the multiverse might be sterile, unable to support any form of life, but there will be some universes, perhaps rare but still infinite in number, because the multiverse is infinite, where the constants happen to allow for stars and planets and chemistry and ultimately life. We necessarily find ourselves in one of those rare universes. This explanation is unsatisfying to some people. It seems to give up on finding a deeper reason for the constants, accepting them as random chance. Others find it liberating, a reminder that the universe doesn't exist for our benefit, that we're here by accident rather than design, and that this makes our existence all the more precious and remarkable. There's also the possibility that the constants are not independent, but are related by some deeper theory we haven't discovered yet. Perhaps there's only one mathematically consistent set of values they can have, or perhaps there's a physical mechanism that sets them to particular values. String theory suggests that the constants we observe are determined by how extra dimensions are compactified, and maybe there's a reason why those dimensions take the particular shape they do in our universe. We should also remember that life as we know it might not be the only kind of life possible. We're made of carbon chemistry, dissolved in water, powered by the energy from a main sequence star. But could there be other forms of life based on different chemistry, different energy sources, different environments? If so, then the range of life-permitting universes might be much wider than we think. Silicon-based life has been proposed, though carbon seems much more versatile for building complex molecules. Life in the cold darkness of interstellar space, powered by cosmic rays or magnetic fields, is harder to imagine but not impossible in principle. Perhaps in other universes with different laws, forms of life utterly unlike anything we can conceive might exist. The Anthropic Principle reminds us that our perspective is limited. We see the universe from one tiny corner of space and time, with minds shaped by evolution to survive on a particular kind of planet. Our intuitions might mislead us when we try to think about ultimate questions, but we can try to see beyond our limitations, to imagine possibilities we haven't thought of yet. For centuries, philosophers and theologians have argued about whether the universe needs a cause. The Cosmological Argument, in its various forms, claims that everything that exists must have a cause, and tracing causes back leads ultimately to a first cause, often identified with God. Let's explore this argument and how modern cosmology relates to it. The argument goes something like this. Everything we observe in the universe has a cause. Your coffee cup exists because someone made it. You exist because of your parents. The Earth exists because of the solar nebula from which it formed. If we trace causes backward, we get a chain of causes, each event caused by a previous event. But this chain cannot go back infinitely, the argument claims, because an infinite regress is impossible or unsatisfying. Therefore, there must be a first cause, something that started the chain without itself being caused. This first cause, the argument continues, must be different from everything else in the universe. It must be uncaused, necessary rather than contingent, eternal and outside of time. These qualities traditionally are attributed to God. Modern cosmology both challenges and complicates this argument. On one hand, the Big Bang might seem to support it. If the universe had a beginning 13.8 billion years ago, then something must have caused that beginning, right? Many people find the Big Bang congenial to religious belief for this reason. But there are problems with applying the cosmological argument to the Big Bang. First, as we've discussed, time itself might have begun with the Big Bang. If there's no time before the Big Bang, then the concept of causation breaks down, because causation requires time. A cause must come before its effect. If there's no before, there can be no cause. Second, quantum mechanics has shown us that not everything needs a cause. Radioactive decay happens randomly, with no cause for any particular decay event. Particles pop into existence in the quantum vacuum without any cause. The universe, at its most fundamental level, is probabilistic rather than deterministic. So the premise that everything must have a cause is false, at least in the classical sense of causation. Third, even if the Big Bang required a cause, it doesn't follow that this cause is God in the traditional sense. It could be a quantum fluctuation in a pre-existing quantum field. It could be a bounce from a previous universe. It could be something we haven't thought of yet. Jumping from the universe has a cause to God exists requires additional arguments that the cosmological argument alone doesn't provide. That said, the cosmological argument does point to a real question. Why is there something rather than nothing? Even if quantum mechanics allows things to pop into existence without a cause, it still requires the laws of quantum mechanics, the quantum fields. The structure of space-time. Where did those come from? Some physicists argue that the laws of physics are necessary, that they couldn't be otherwise, that mathematics itself determines what must exist. From this view, asking why the laws of physics exist is like asking why 2 + 2 = 4. It's just a necessary truth, not something that requires explanation. Others argue that even necessary mathematical truths need some kind of ground or explanation, some reason why these particular mathematical structures are instantiated in reality rather than others. This gets into deep philosophical territory about the relationship between mathematics and physical reality. David Hume, the Scottish philosopher, challenged the cosmological argument back in the 18th century by questioning why we need a first cause at all. Why can't the chain of causes extend infinitely into the past? Our minds rebel at the idea of infinity, but that doesn't make it impossible. Maybe the universe, or the multiverse, is simply eternal, with no beginning and no need for a first cause. Modern eternal inflation theories support this possibility. If inflation is eternal into the past, there was no first moment, no beginning that requires explanation. The multiverse has always existed, always been creating new bubble universes. Our particular universe had a beginning, but the multiverse didn't. Of course, this just pushes the question back. Why does the eternally inflating multiverse exist? Why inflation? Why quantum mechanics? We haven't escaped the fundamental mystery. We've just relocated it. Some philosophers argue that this is inevitable, that there must be something that exists without explanation, some brute fact that we just have to accept. Whether that's God, or the laws of physics, or the quantum vacuum, or mathematical structures, something has to be foundational, not explained by anything else. The cosmological argument, in the end, might not prove God's existence, but it does point to the deep strangeness of existence itself. That there is something rather than nothing is not a trivial fact. It's the most astonishing fact of all, and whether we explain it through physics, philosophy or theology, the wonder remains. One of the most mind-bending ideas in modern cosmology is that the universe might have created itself. This sounds paradoxical, like pulling yourself up by your own bootstraps or being your own grandfather. But let's explore what physicists mean by this and whether it makes any sense. Stephen Hawking and James Hartley proposed an idea called the no-boundary proposal in the 1980s. They were trying to apply quantum mechanics to the universe as a whole, to describe the quantum state of the entire cosmos. Their idea involves a concept from quantum mechanics called imaginary time. In ordinary time, which physicists call real time, events are ordered from past to future. But in quantum mechanics, you can do calculations using imaginary numbers involving the square root of -1. When you use imaginary time in general relativity, space-time can have different properties than it does in real time. Hawking and Hartle suggested that in imaginary time, the universe has no boundary, no edge, no beginning point. Think of the surface of the Earth. If you travel south, you eventually reach the South Pole, but the South Pole is not an edge or a boundary. It's just the southernmost point. You can't go any further south, but there's no wall, no discontinuity, just a smooth surface. Similarly, in imaginary time, the universe might be finite but without a boundary. If you go back in time, you eventually reach the earliest moment, but that moment is not a singularity or a beginning in the usual sense. It's just the earliest point in a smooth, four-dimensional space-time. When you transform back from imaginary time to real time, the ordinary time we experience, the universe appears to have a beginning, the Big Bang. But this beginning is not a moment of creation out of nothing. It's a smooth point in a larger geometric structure. The universe, in a sense, creates itself through the mathematics of quantum gravity. This is highly abstract, and even Hawking admitted that the physical interpretation is unclear. What does it mean for time to be imaginary? How do we get from the mathematical description to physical reality? These are open questions. Another way the universe might create itself involves quantum mechanics and the nature of causality. In quantum mechanics, particles can influence each other in ways that seem to violate our usual notions of cause and effect. There are experiments where a measurement in the present seems to determine what happened in the past, a phenomenon called retrocausality. If the universe itself is a quantum system, maybe its existence in the present creates the conditions for its origin in the past. This sounds wildly paradoxical. But quantum mechanics is full of apparent paradoxes that nevertheless turn out to be true. John Wheeler, one of the great physicists of the 20th century, proposed something he called the participatory universe. He suggested that observers, conscious beings like us, play a role in bringing the universe into existence through the act of observation. This is an extreme interpretation of quantum mechanics, and most physicists don't accept it, but Wheeler was serious about the idea. From this perspective, the universe creates itself through a kind of loop. The Big Bang creates space and time and matter. Matter organizes into stars and planets. On some planets, life emerges. Life evolves into conscious observers. Observers, through the act of observing, collapse the quantum wave function of the universe, determining what happened in the past, including the Big Bang itself. The universe bootstraps itself into existence. This is deeply strange, and it's not clear whether it even makes logical sense. How can the universe exist before observers if observers are needed to bring it into existence? It seems to require a kind of retrocausal loop that might be incoherent, but quantum mechanics has taught us to be humble about our intuitions. Things that seem impossible, like particles being in two places at once, or influencing each other faster than light, turn out to be real. Maybe the universe creating itself is equally strange, but equally real. A simpler interpretation is that the universe doesn't need to create itself, because it has always existed in some form. The multiverse of eternal inflation, or a cyclic universe that bounces from expansion to contraction and back, or even a block universe where all of time exists eternally, these all avoid the need for an origin at all. But the phrase, "the universe created itself," might mean something less dramatic. Maybe it just means that the universe emerged from something simpler through natural processes, with no external creator needed. A quantum fluctuation in the vacuum, allowed by the laws of physics, grew into our universe through inflation. The laws of physics, in this sense, created the universe. Of course, this raises the question of where the laws of physics came from. Some physicists and philosophers argue that the laws are necessary, that they could not be otherwise, and that necessary truths don't require creation or explanation. Others argue that even necessary truths need grounding in something deeper, perhaps in mathematics itself or in some more fundamental reality. There's a humility in admitting that we might not be able to answer this question, at least not yet. The origin of the universe pushes against the limits of science, philosophy, and human understanding. But the fact that we can ask the question, that we can develop theories and test them and think carefully about what self-creation might mean, is itself remarkable. Mathematics plays a central role in physics, so much so that some physicists and philosophers argue that the universe is fundamentally mathematical. Let's explore this idea and what it might tell us about why the universe exists. When physicists describe the universe, they use equations. Einstein's field equations describe how matter curves space-time. Schrödinger's equation describes how quantum wave functions evolve. Maxwell's equations describe electromagnetism. These equations are not just useful tools or approximations. They seem to capture something deep and true about reality itself. And the mathematics is often discovered before the physics. Complex numbers were invented by mathematicians centuries before quantum mechanics showed they were essential to describing reality. Non-Euclidean geometry was developed as an abstract curiosity before Einstein showed that space-time is curved. Group theory, developed for pure mathematical reasons, turned out to be the perfect language for particle physics. This has led some people to wonder whether mathematics is discovered or invented. Do we create mathematical concepts, or do we find them existing in some abstract realm? Platonists argue that mathematical objects exist independently of human minds, in a realm of perfect eternal forms. Mathematicians explore this realm, discovering truths that were always there. If mathematics exist independently of physical reality, then maybe physical reality is an expression of mathematics. The physicist Max Tegmark has proposed the mathematical universe hypothesis, which claims that our external physical reality is a mathematical structure, not just described by mathematics, but literally is mathematics. From this perspective, the question, why does the universe exist, becomes, why does this particular mathematical structure exist? And if all mathematical structures exist in the Platonic realm, then all possible universes exist. The multiverse is not just physical but mathematical, an infinite library of all possible mathematical structures, each one a universe. Our universe, from this view, is one particular mathematical structure, one set of equations and symmetries and relationships. We exist in this structure rather than others because this one permits conscious observers. The Anthropic Principle applies, but now to a mathematical multiverse rather than a physical one. This is a beautiful idea, elegant and all-encompassing. It dissolves the mystery of existence by making existence necessary for all mathematical structures. It's not that our universe was created or sparked into being, it exists because the mathematics exists, and mathematics exists necessarily by its very nature. But there are problems with this view. One is the problem of consciousness. If the universe is just mathematics, where does subjective experience come from? Mathematics is abstract, timeless, without qualities or feelings. Yet we experience redness and pain and joy. Qualitative aspects of reality that don't seem to be captured by equations. Another problem is determining which mathematical structures correspond to physical reality. Not all mathematical structures are consistent or well-defined. Some lead to contradictions. Some are too simple to contain any complexity. Somehow, physical reality selects certain mathematical structures and not others, or at least makes some structures more real to us than others. And there's the question of why mathematics works so well in the first place. Eugene Wigner, a physicist and mathematician, wrote a famous essay called Quote 25, He was puzzled by the fact that mathematical concepts developed for purely abstract reasons turn out to describe the physical world with astonishing precision. Why should nature care about our mathematics? Why should the universe be comprehensible to us at all? These are deep questions that the mathematical universe hypothesis might answer, but it's not clear that it does so satisfactorily. Some philosophers argue that mathematics is a human creation, a language we've developed to describe patterns we observe. From this view, the effectiveness of mathematics is not surprising because we've tailored our mathematics to fit the world we see. If the world were different, we would develop different mathematics. But this view has trouble explaining why mathematics predicts things we haven't observed yet. General relativity predicted the bending of light by gravity before it was measured. Quantum mechanics predicted the existence of antimatter before it was discovered. The Higgs boson was predicted by mathematical symmetry arguments decades before it was found. How can a human invention predict unknown features of reality? Perhaps the truth is somewhere in between. Mathematics is a human creation, but it's constrained by the structure of reality. We invent mathematical concepts, but only certain concepts turn out to be useful or true, because reality has a particular structure that limits what works. Mathematics is a joint creation of human minds and the external world. However we resolve these questions, the relationship between mathematics and physics is profound. The fact that abstract thought can reveal the workings of the cosmos, that symbols on paper can predict the motion of galaxies or the outcome of particle collisions, is one of the great mysteries and wonders of existence. Maybe the universe exists because existence is a mathematical necessity. Or maybe mathematics is just our best map of a territory that transcends any description. Either way, the connection between thought and reality, between mind and cosmos, is beautiful and strange. As we've explored theories of quantum mechanics, cosmology, and the nature of time, a deeper question has been lurking beneath the surface. What is real? What does it mean for something to exist? Let's think about these questions carefully, because they might help us understand what the Big Bang really was. In our everyday lives, we think we know what's real. Tables and chairs are real. People are real. The planet beneath our feet is real. But modern physics has challenged these simple certainties at every turn. Atoms, we now know, are mostly empty space. The solid objects around us are actually clouds of electrons surrounding tiny nuclei, held together by electromagnetic forces. When you touch a table, you're not really touching it in the sense of contact. The electrons in your hand repel the electrons in the table, creating a sensation of solidity, but there's no actual contact. It's all force fields and quantum mechanics, and atoms themselves are not the fundamental building blocks they once seemed to be. Protons and neutrons are made of quarks, held together by gluons. But quarks and gluons might themselves be excitations of quantum fields, vibrations in the fundamental fabric of space-time. The deeper we look, the more reality seems to dissolve into mathematics and fields and relationships rather than things. Quantum mechanics makes this even stranger. Before you measure a particle's position, it doesn't have a definite position. It exists in a superposition of many possible positions. Only when you measure does it collapse into one specific location. This is not just ignorance on our part. The particle genuinely doesn't have a definite position until measured. Reality, at the quantum level, is fundamentally probabilistic and dependent on observation. This raises profound questions about the nature of reality. Is something real if it's not observed? Do quantum particles exist in a definite state before measurement, with our measurements just revealing a pre-existing reality? Or does measurement actually create reality, collapsing the wave function and making one possibility actual out of many potential outcomes? Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, says that quantum systems don't have definite properties until measured. The measurement creates reality. The many worlds interpretation, proposed by Hugh Everett, says that all possible outcomes are real, each one existing in a different branch of reality, a different universe. When you measure a particle's position, the universe splits into multiple versions, one for each possible outcome. The pilot wave theory, advocated by Louis de Broglie and David Bohm, says that particles do have definite positions all along, guided by a wave that we can't directly observe. Measurement just reveals what was always there. Each interpretation makes the same predictions for experimental results, so we can't distinguish between them through experiment alone. They're different metaphysical pictures of the same mathematical formalism. This situation is deeply unsettling for people who want clear answers about what's real. The truth is, we don't know. Physics tells us how to predict the outcomes of experiments with extraordinary precision, but it doesn't tell us what's really happening behind the scenes. Nature at its most fundamental level might be genuinely strange, resistant to our attempts to fit it into familiar categories. How does this relate to the Big Bang? Well, if reality is not as solid and definite as we thought, if existence itself is something that emerges from quantum processes or mathematical structures or acts of observation, then the question of what sparked the Big Bang might need rethinking. Maybe the Big Bang was not a moment when nothing became something, but a moment when quantum potentiality became classical actuality. Before the Big Bang, there was no definite state, just a quantum superposition of many possible universes. The Big Bang was the moment when one possibility became real, perhaps through some cosmic measurement or observation. Or maybe, in the many worlds interpretation, all possible Big Bangs happened, each one creating a different universe, and we simply find ourselves in one particular branch. There was no single spark, no single beginning, but an infinite branching of possibilities, all equally real. Or maybe the whole question rests on a mistaken assumption that there's a sharp distinction between existence and non-existence, between something and nothing. Perhaps reality is more of a spectrum, with different degrees or kinds of existence. Mathematical structures exist in one way, physical objects in another, conscious experiences in yet another. The Big Bang might mark a transition between different modes of existence, rather than a transition from non-existence to existence. These are the kinds of questions that physics alone cannot answer. They venture into philosophy, into metaphysics, into the realm of questions that might not have definite answers, but they're worth thinking about because they remind us that our familiar categories might not apply at the extremes of reality, at the very beginning or the very small or the very strange. The physicist Richard Feynman once said that if you think you understand quantum mechanics, you don't understand quantum mechanics. The same might be true of existence itself. If we think we understand what it means for something to be real, we probably don't understand it as deeply as we think. The universe is teaching us humility, showing us that reality is stranger and more wonderful than our everyday experience suggests. There are some questions that might not have answers, at least not answers we can find. Let's explore the limits of what we can know about the universe and its origin, and think about what that means for our question. Science has been extraordinarily successful at answering questions about the natural world. We've figured out how planets orbit, how stars shine, how life evolves, how atoms bond into molecules. We've sent spacecraft to other planets, cured diseases, developed technologies that would seem like magic to our ancestors. It's tempting to think that science can answer any question, given enough time and resources, but there are fundamental limits to what we can know. Some of these limits are practical. The Planck scale, where quantum gravity becomes important, requires energies we might never be able to achieve. Building a particle accelerator powerful enough to probe Planck scale physics would require more energy than exists in the observable universe, so we might never be able to directly test our theories of quantum gravity. Other limits are more fundamental. Gödel's incompleteness theorems, proved by the mathematician Kurt Gödel in the 1930s, show that any sufficiently complex mathematical system contains statements that are true but cannot be proven within that system. There are mathematical truths that we can never prove, no matter how much time we spend or how clever we are. Physics might have similar limits. There might be true facts about the universe that we can never verify through observation or experiment. The interior of a black hole is causally disconnected from the outside universe. Information about what happens inside can never reach us. Other universes in the multiverse, if they exist, might be forever beyond our ability to observe. The question of what sparked the Big Bang might fall into this category. If time itself began with the Big Bang, then before might be meaningless, and the question might be unanswerable not because we're not clever enough, but because there's no answer to find. It's like asking what sound the colour blue makes. The question itself is confused, mixing categories that don't mix. Or if the multiverse is real, and our Big Bang was just one bubble nucleating in an eternally inflating space, we might never be able to observe the larger multiverse. The evidence would be forever beyond our cosmic horizon, unreachable because space is expanding faster than light can travel. We could have good theoretical reasons to believe in the multiverse, but we might never be able to prove it definitively. This doesn't mean we should give up on asking questions or doing science. Even if we can't answer every question, we can still make progress on the questions we can answer. We can test theories, make predictions, refine our understanding. We can push the boundaries of knowledge outward, even if those boundaries might never disappear completely. And there's something valuable in recognizing the limits of our knowledge. It keeps us humble. It reminds us that reality doesn't owe us explanations. The universe existed for billions of years before humans appeared, and it will continue long after we're gone. It's not here for our benefit, and it's not obligated to make sense to us. At the same time, we should be cautious about declaring something unknowable. History is full of examples of questions that seemed unanswerable but were eventually solved. The nature of stars, the age of the Earth, the origin of species, all were mysteries that seemed beyond science's reach at one time. Then new methods, new instruments, new ideas opened them up. Maybe the origin of the universe will be the same. Maybe a future theory of quantum gravity will let us understand what happened at the Planck EP. Or maybe new observations will give us evidence about the multiverse or the pre-Big Bang state. We should remain open to the possibility of progress while accepting that some questions might remain mysteries. There's also a difference between practical unknowability and fundamental unknowability. Practically, we might never be able to visit another galaxy, or measure the position of an electron with Planck scale precision. But fundamentally, these things have answers. There is a fact of the matter, even if we can't access it. The question of what sparked the Big Bang might be fundamentally unanswerable if the question itself is malformed. Or it might be practically unanswerable because the evidence is beyond our reach. Or it might be answerable in principle and even in practice, once we develop the right theories and tools. We don't yet know which category it falls into. Living with this uncertainty is part of the human condition. We're creatures with powerful minds that can ask questions our current knowledge cannot answer. We can imagine possibilities we cannot verify. We can think about the infinite and the eternal and the impossible. This can be frustrating, but it can also be wonderful. The questions we can't yet answer are signposts pointing toward the future, toward discoveries we haven't made yet. We've focused mainly on the standard Big Bang theory and inflation, but there are other ideas about how the universe began. Let's explore some of these alternative theories and see what they suggest about cosmic origins. One alternative is the cyclic model, which suggests that the universe goes through endless cycles of expansion and contraction. In this model, our Big Bang was not the absolute beginning, but the bounce from a previous contracting phase. The universe collapsed into a very dense state, then bounced and began expanding again. This cycle might repeat infinitely into the past and future. The cyclic model has some attractive features. It avoids the Singularity Problem by replacing the Big Bang with a bounce. It provides a natural explanation for why the universe exists. It always has, in some form. And it might explain why the universe appears fine-tuned for life. If there have been many cycles, perhaps the constants and laws evolve or vary from cycle to cycle, and we find ourselves in a cycle that permits observers. but the cyclic model faces challenges. General relativity predicts that entropy, disorder, increases over time. If the universe has been cycling forever, where did the low entropy state of our current cycle come from? Each cycle should be more disordered than the last, but observations show that our universe is remarkably ordered. The cyclic model needs some mechanism to reset entropy between cycles, and finding such a mechanism has proved difficult. Another idea is the steady-state theory, proposed in the 1940s by Fred Hoyle, Hermann Bondi and Thomas Gold. They suggested that the universe has no beginning and no end, but is eternal and unchanging on large scales. As the universe expands, new matter is continuously created to fill the gaps, keeping the overall density constant. The steady-state theory was elegant and philosophically appealing. It avoided the question of cosmic origins entirely by denying that there was an origin. But observations contradicted it. The discovery of the cosmic microwave background radiation, the relic light from a hot, dense early universe, was strong evidence against the steady-state model. The universe clearly was different in the past, hot and dense rather than eternally the same. String theory, our best current candidate for a theory of quantum gravity, has suggested various scenarios for cosmic origins. One is the ekpyrotic model, proposed by Paul Steinhardt and Neil Turok. In this model, our universe is a three-dimensional membrane, or brane, floating in a higher dimensional space. Occasionally our brain collides with another brain, and this collision releases enormous energy, creating what we perceive as the Big Bang. The ekpyrotic model is fascinating because it connects the origin of the universe to the extra dimensions predicted by string theory. It provides a mechanism for the Big Bang that doesn't require a singularity, just a collision in higher dimensions. But like many ideas from string theory, it's difficult to test experimentally. The extra dimensions, if they exist, are compactified into tiny scales we can't observe directly. Loop quantum cosmology, derived from loop quantum gravity, suggests yet another scenario. In this approach, space-time is fundamentally discrete, made of tiny loops at the Planck scale. When you compress the universe during the Big Bang, it can't become smaller than these fundamental units. The universe reaches a maximum density and then bounces, transitioning from a contracting phase to an expanding phase. This big bounce replaces the Big Bang singularity with a smooth transition. Time extends infinitely into the past, with our current expanding phase preceded by a contracting phase. Loop quantum cosmology makes specific predictions about the cosmic microwave background that might be testable with future observations. There are also more speculative ideas. The simulation hypothesis suggests that our universe might be a computer simulation run by a more advanced civilization. From this perspective, the Big Bang is not a physical event but the start of the simulation. This idea is fun to think about but difficult to take seriously as science, because it makes few testable predictions and raises more questions than it answers. The holographic principle, inspired by black hole thermodynamics and string theory, suggests that our three-dimensional universe might be a projection from information encoded on a two-dimensional boundary. The Big Bang, in this view, might be a holographic phenomenon, with the true physics occurring on a lower dimensional surface. This is deeply strange and still being developed by physicists. Each of these theories attempts to address the same fundamental questions. Why does the universe exist? What came before? What laws govern the earliest moments? But they approach these questions from different angles, making different assumptions, prioritizing different pieces of evidence. The fact that we have multiple competing theories is both frustrating and exciting. It's frustrating because we don't yet know which, if any, is correct. But it's exciting because it shows that science is alive and active, with creative minds exploring different possibilities. Eventually, observations will help us narrow down the options, ruling out theories that make wrong predictions and supporting those that match what we see. Until then, we should hold these theories lightly, appreciating them as different perspectives on the same deep mystery. Each one teaches us something about the possibilities, about what might have been or could be, and each one reminds us that the universe is stranger and more wonderful than we yet understand. Perhaps we should step back and think about why we care so much about this question in the first place. What is it about origins that captures the human imagination? Why do we need to know where we came from? Every culture in human history has had origin stories. Creation myths from Mesopotamia, Egypt, Greece, China, the Americas, Africa, all tell stories about how the world began. These stories are often beautiful, poetic, filled with meaning and symbolism. They speak to deep human needs for understanding and belonging. The Babylonian creation myth, the Enuma Elish, describes the world being created from the body of a defeated goddess. The Hindu tradition speaks of cycles of creation and destruction, with the universe breathing in and out through eternity. The biblical account in Genesis describes creation in 6 days, with humanity as the pinnacle. Indigenous Australian traditions speak of the dream time, a mythological time when the world was shaped by ancestral beings. These stories are not primarily about scientific facts. They're about meaning, purpose, and humanity's place in the cosmos. They answer questions like, why are we here? What is our relationship to the natural world? What gives life value and purpose? Modern cosmology, with its story of the Big Bang and cosmic evolution, is sometimes called our scientific creation myth. But there's a crucial difference. Scientific theories must make testable predictions and can be proven wrong by observation. Creation myths, in contrast, are accepted through faith and cultural tradition. Yet there's something mythic about the Big Bang story nonetheless. The idea of everything emerging from an infinitely dense point, of space and time themselves coming into existence, of the entire universe evolving from simplicity to complexity over billions of years. This is a story of cosmic significance. It speaks to our sense of wonder and awe. Why do we seek origin stories? Perhaps because knowing where we came from helps us understand who we are. If the universe was created with purpose, then our lives might have purpose too. If the universe is an accident, a quantum fluctuation that just happened to occur, that suggests a different relationship between ourselves and reality. There's also something satisfying about tracing effect back to causes, about understanding the chain of events that led to the present moment. It gives us a sense of coherence, of the world making sense. The idea that some things might not have causes, or that the chain of causation might loop back on itself or extend infinitely, is unsettling. Children ask why repeatedly, driving their parents to frustration. Why is the sky blue? Because of how light scatters. Why does light scatter? Because of the properties of air molecules. Why do air molecules have those properties? Because of quantum mechanics. Why does quantum mechanics work that way? Eventually we reach the limits of our knowledge, and the only honest answer is we don't know yet, or even we might never know. Adults, in a sense, never stop asking why. Scientists ask why the universe expands, why gravity exists, why the fundamental constants have the values they do. Philosophers ask why there is something rather than nothing, why the laws of nature are the way they are, why we're conscious. Theologians ask why God created the world, why suffering exists, why we're here. These questions might not all have answers, but asking them is part of what makes us human. We're creatures who seek meaning and understanding. We look at the night sky and wonder. We ask questions that our ancestors couldn't even formulate. We push against the boundaries of knowledge, trying to see beyond what we know into what we don't yet understand. The question of what sparked the Big Bang is one of these boundary questions. It sits at the edge of science and philosophy, touching on physics and metaphysics, observation and speculation. We might never answer it definitively, but the asking itself is valuable. It forces us to think carefully about time, causation, existence, and reality. It pushes scientists to develop better theories and make better observations. It reminds philosophers to sharpen their concepts and arguments. It invites everyone to contemplate the deepest mysteries of existence. And perhaps most importantly, it cultivates a sense of humility and wonder. We're tiny creatures on a small planet orbiting an ordinary star in an ordinary galaxy. We've only been around for a cosmic instant, yet we can think about the origin of everything, can formulate theories about what happened in the first fraction of a second after the Big Bang, can ask questions about the nature of time and space and existence itself. That's extraordinary. That's worth celebrating, even if we never find all the answers we seek. Let's think about what it means to be comfortable with mystery, to accept that some questions might not have answers, and to find peace in the not knowing. In our culture, there's often pressure to have answers, to be certain, to know things definitively. Admitting ignorance can feel like failure. We're taught to solve problems, to figure things out, to master our subjects. Uncertainty makes us uncomfortable. But some of the wisest people throughout history have embraced not knowing. Socrates famously said that wisdom begins with recognizing your own ignorance. The Taoist tradition speaks of the value of emptiness and unknowing. Buddhist meditation practices often involve letting go of the need to understand and simply being present with what is. Scientists, despite their reputation for certainty, actually live with uncertainty constantly. Every scientific theory is provisional, subject to revision or replacement if new evidence comes along. The greatest scientists are those who can hold their ideas lightly, willing to abandon them if they turn out to be wrong. Richard Feynman spoke beautifully about living with doubt. He said that it's okay to not know, that you can live with uncertainty without being paralyzed by it. He argued that having questions you cannot answer is better than having answers you cannot question. The mystery of what sparked the Big Bang might be one of those questions that we cannot fully answer, at least not yet and perhaps not ever, and that's okay. We can still investigate, still theorize, still observe and experiment. But we can do so without demanding certainty, without needing a final, definitive answer. There's a kind of freedom in accepting mystery. It releases us from the burden of needing to know everything. It allows us to be curious without being anxious. We can explore without needing to conquer. We can ask questions without needing to solve every problem. This doesn't mean we should be satisfied with ignorance or stop searching for answers. The scientific endeavour is about pushing back the boundaries of the unknown, learning more about how the universe works. But we can pursue knowledge while also accepting that complete knowledge might be impossible, that some mysteries might remain no matter how hard we try. In fact, mystery might be essential to wonder. If we understood everything completely, would the universe still fill us with awe? Part of what makes the cosmos beautiful is its strangeness, its resistance to easy explanation, its ability to surprise us. The quantum world is mysterious. We can predict its behaviour with extraordinary precision, but we don't fully understand why it works the way it does or what's really happening at the deepest level. Yet this mystery doesn't diminish quantum mechanics. If anything, it makes it more fascinating. The same is true of consciousness. We're made of atoms obeying the laws of physics, yet we have subjective experiences, feelings, awareness. How does matter become mind? We don't know. There are theories, but no consensus, no complete explanation. Yet we don't let this mystery prevent us from studying the brain or thinking about the mind. The origin of the universe might be similar. We can study the Big Bang, trace the evolution of the cosmos, understand much about how the universe works. But the ultimate question of why there is something rather than nothing, or what sparked everything into being, might remain mysterious. And maybe that's appropriate. Maybe the universe is entitled to its secrets. Maybe there are things we're not meant to know, not because they're forbidden, but because they're beyond the reach of our current methods, or even our current concepts. This requires a certain kind of intellectual humility. We have to acknowledge that we're finite beings trying to understand an infinite cosmos, that our minds are shaped by evolution to survive on Earth rather than to comprehend ultimate reality, that we've only been asking these questions for a few thousand years and might need much longer to find answers, But humility doesn't mean resignation. We can be humble about what we know while still being ambitious about what we want to learn. We can accept our limitations while still pushing against them. We can be comfortable with mystery while still seeking to unravel it. There's a balance here between knowing and not knowing, between certainty and doubt, between accepting mystery and pursuing understanding. Finding that balance is part of the human journey, part of what makes us thoughtful beings rather than just biological machines. As we think about the Big Bang and its origin, we can hold multiple possibilities in mind without needing to choose one definitively. Maybe it was a quantum fluctuation. Maybe it was a bounce from a previous universe. Maybe time began at the Big Bang and there is no before. Maybe there's an infinite multiverse. Maybe we'll discover something entirely new that we haven't thought of yet. All of these are possible. None is certain, and that's okay. We can explore them all, test them where possible, think about them carefully, and remain open to surprise. While we've spent a lot of time thinking about what we don't know, it's worth pausing to appreciate what we do know. Our understanding of the universe has grown enormously in the past century, and the knowledge we've gained is extraordinary. We know that the universe is expanding. Edwin Hubble discovered this in the 1920s by observing that distant galaxies are moving away from us, with farther galaxies moving faster. This isn't because we're at the centre of anything. Every point in the universe sees the same pattern. Space itself is expanding, carrying galaxies along with it. We know that this expansion means the universe was smaller in the past. If we run the clock backward, we can trace the universe to a time when it was incredibly hot and dense. This is the Big Bang, and it happened approximately 13.8 billion years ago. We know this age with remarkable precision, accurate to within a few tens of millions of years. We know what the universe is made of. About 5% is ordinary matter, the stuff of atoms and molecules, stars and planets and people. About 27% is dark matter, a mysterious substance that interacts gravitationally but doesn't emit light. We know it's there because we can see its gravitational effects on galaxies and the cosmic microwave background. About 68% is dark energy, an even more mysterious component that's causing the expansion of the universe to accelerate. We know the universe is geometrically flat. If you draw a triangle on the larger scales, the angles add up to exactly 180 degrees. This tells us something about the density of the universe and supports the idea that cosmic inflation occurred in the early universe. We know that the cosmic microwave background radiation exists, filling all of space with a faint glow that's the relic of the Big Bang. We've mapped this radiation in extraordinary detail, and it tells us about the conditions in the early universe just a few 100,000 years after the Big Bang. We know that the elements were formed in the Big Bang and in stars. Hydrogen and helium were created in the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis. Heavier elements, from carbon to iron, were created in the cores of stars through nuclear fusion. Elements heavier than iron were created in supernova explosions and neutron star collisions. We know that galaxies formed from tiny density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter through gravity, growing over time into the galaxies we see today. The pattern of these fluctuations is imprinted in the cosmic microwave background, and we can trace the evolution from those tiny seeds to the vast cosmic web of galaxies we observe. We know that stars live and die, transforming hydrogen into heavier elements, enriching the cosmos with the raw materials for planets and life. Our own sun is a third-generation star, made from material that was once inside earlier stars that lived and died billions of years ago. We know that the fundamental forces of nature were unified in the extremely early universe and separated as the universe cooled. We understand these forces with extraordinary precision through the standard model of particle physics and general relativity. We know that quantum mechanics governs the behaviour of the very small, and that general relativity governs the behaviour of the very large. These theories have been tested countless times and have never been proven wrong within their domains of applicability. We know that information about the early universe is preserved in various ways. The cosmic microwave background is one source. The abundances of light elements is another. The pattern of galaxy clustering is a third. These different sources of information all point to the same picture of cosmic history, giving us confidence that we're on the right track. This is an astonishing amount of knowledge for creatures who have only been asking scientific questions for a few centuries. Our ancestors looked at the night sky and saw gods and myths. We look at the same sky and see a 13.8 billion-year-old universe, expanding and evolving according to mathematical laws we've discovered. We've sent telescopes into space that can look back to when the universe was just a few 100 million years old, seeing the first galaxies forming. We've built particle accelerators that recreate the conditions of the early universe, testing our theories of how matter behaves at extreme energies. We've detected gravitational waves, ripples in space-time predicted by Einstein a century ago, opening a new window on the cosmos. None of this answers the ultimate question of what sparked the Big Bang. We still don't know why there is something rather than nothing, or what happened at the very first instant, or whether the universe had a true beginning or has existed in some form forever. But the progress we've made is real and significant. We understand so much more than we did a century ago, or even a decade ago. Each generation of scientists pushes the boundaries of knowledge a little further, asking better questions, developing better theories, making better observations. And the search continues. New telescopes are being built, new experiments are being designed, new theoretical frameworks are being developed. The James Webb Space Telescope is revealing the early universe in unprecedented detail. Gravitational wave detectors are becoming more sensitive. Particle physicists are planning the next generation of accelerators. We don't know where this will lead. We might answer the question of what sparked the Big Bang, or we might discover that the question itself needs reformulating, or we might find that it's beyond our ability to answer. But whatever we discover will be worth knowing, will deepen our understanding, will reveal new wonders we haven't imagined yet. The universe is extraordinarily generous with its secrets. Every time we think we've reached a dead end, a new path opens up. Every time we solve one mystery, we discover new mysteries waiting to be explored. The more we learn, the more we realize how much there is to learn. As we near the end of our journey together through this profound mystery, let's take a moment to appreciate not the answers but the question itself, because there's something deeply beautiful about the fact that we can ask what sparked the Big Bang if there was nothing. Think about what the question represents. Here we are, arrangements of atoms on a small planet, made of matter that was forged in the cores of ancient stars, contemplating the origin of absolutely everything. We're using brains built by evolution for survival on the African savanna to think about the first fraction of a second of cosmic time. We're asking questions that push against the very limits of comprehension. The question connects us to something larger than ourselves. When you wonder about the Big Bang, you're joining a conversation that stretches back through centuries of human thought. Ancient Greek philosophers asked similar questions about ultimate origins. Medieval scholars debated whether the universe had a beginning. Modern scientists developed the theories and made the observations that transform these philosophical questions into scientific ones. You're also part of a global community of curious minds. Around the world, right now, people are asking the same question. Scientists in laboratories, students in classrooms, philosophers in universities, people lying in bed at night looking up at the ceiling, wondering. The question connects us across time and space, part of humanity's collective effort to understand our place in the cosmos. There's also something poetic about the question's structure. Quote 31. Each word carries weight. Quote 32 suggests a trigger, a beginning, but also something small and fragile, like a match flame in darkness. Quote 33 is a name that almost trivializes the most important event in history. Yet it captures something essential about rapid expansion and transformation. Quote 34 is a word that points towards something our minds cannot quite grasp. absolute absence, impossible to imagine yet somehow meaningful. The question is a koan, like the puzzles used in Zen Buddhism to break through ordinary thinking. The Zen master asks. The question seems nonsensical, but wrestling with it can lead to insight. Similarly, asking what came before time or what caused the first cause pushes our thinking beyond its normal patterns, forcing us to confront the limits of logic and language. And there's beauty in the way the question reveals our relationship with the universe. We are not separate from the cosmos, looking at it from outside. We're part of it, made of the same matter, governed by the same laws. When we ask about the Big Bang, the universe is in some sense asking about its own origins through us. We're the universe becoming self-aware, conscious matter contemplating its source. This perspective is humbling but also elevating. We're tiny, yes, insignificant on cosmic scales. But we're also extraordinary, the rare parts of the universe that can think and wonder and ask questions. Consciousness might be common in the cosmos, or it might be incredibly rare. We don't know. But either way, the fact that matter can organize itself into patterns that think and feel and question is remarkable. The question also highlights the peculiar human ability to think about things we cannot directly experience. We've never seen the Big Bang. We weren't there. It happened billions of years before we existed. Yet we can reason about it, construct theories, make predictions, test them against observations. We can think about times and places and conditions utterly unlike anything in our experience. This is the power of abstraction, of mathematics, of scientific thinking. We can extend our minds beyond the immediate and observable into the distant past and future, into the very small and the very large, into realms that would be completely alien to our senses if we could visit them. And the question invites us to think about meaning and purpose. Does the universe have a reason for existing? Are we here by chance or by design? Is there something rather than nothing because of random quantum fluctuations? Or is there a deeper explanation? These aren't purely scientific questions. They touch on philosophy, theology, and personal meaning. Different people will answer differently, and that's okay. The question is large enough to accommodate multiple perspectives. Scientists can approach it through physics and cosmology. Philosophers can explore it through logic and metaphysics. Theologians can contemplate it through their various traditions. Poets can wonder about it in verse. Each approach offers something valuable. Each illuminates a different aspect of the mystery. What makes the question beautiful is not that it has an easy answer, but that it doesn't. It remains open, inviting, challenging. It reminds us that the universe is not yet fully known, that mystery remains, that there are still frontiers to explore and discoveries to make. Every generation inherits the question and adds to our understanding, passing it on to the next generation enriched by new knowledge but still fundamentally mysterious. Perhaps it will always be this way. Perhaps the question of ultimate origins will remain at the edge of human knowledge, forever receding as we approach it, like the horizon. And maybe that's perfect. Maybe a universe that explains itself completely would be less interesting than one that keeps secrets, that invites exploration, that remains mysterious even as we learn more about it. The question, quote, 36, quote, might never be fully answered, but the asking enriches us, deepens our sense of wonder, connects us to the cosmos in the most profound way possible. Let's turn our attention from the question of origins to the universe we actually inhabit. The cosmos as it exists now, unfolding according to laws we can observe and measure, indifferent to our need for ultimate explanations, yet somehow generous in its beauty and complexity. The universe we live in is 13.8 billion years old, vast beyond comprehension, containing billions of galaxies each with billions of stars. It's expanding, cooling, evolving. It follows mathematical laws with extraordinary precision. It permits the existence of stars and planets, chemistry and life, consciousness and thought. None of this depends on us knowing how it began. The universe existed long before humans appeared and will continue long after we're gone. It doesn't need our understanding or approval. It simply is, magnificent and indifferent, operating according to its nature. There's something liberating about accepting this. The universe is not here for us. We're not at the centre of anything. Earth is not special cosmologically, just one planet among trillions. Our sun is an ordinary star in an ordinary galaxy, in an ordinary part of the universe. We exist in the suburbs of the Milky Way, in a quiet neighbourhood far from the dramatic events at the galactic centre. Yet despite our cosmic insignificance, or perhaps because of it, we can appreciate the universe for what it is rather than what we might want it to be. We don't need to be at the centre to matter. We don't need to be created with purpose to have purpose. We can find meaning in our existence even if the universe itself is meaningless. Or we can find meaning in the universe's sheer existence, in the fact that there is something rather than nothing, that matter organises into complex patterns, that consciousness emerges. The universe as it is contains wonders enough to occupy countless lifetimes. Consider a single star like our sun. It's a vast ball of plasma, held together by gravity, powered by nuclear fusion in its core. Every second, it converts millions of tons of hydrogen into helium, releasing energy that travels across space to warm our planet and power life. It's been doing this for 4.6 billion years, and will continue for another 5 billion. The light from our sun takes 8 minutes to reach Earth. When you feel sunlight on your skin, you're feeling energy that was generated in the sun's core through the fusion of hydrogen nuclei, energy that took millions of years to random walk its way from the core to the surface, then travelled through space at the speed of light to reach you. And the atoms in your body, the carbon and oxygen and nitrogen and iron, were all created in stars that lived and died before our sun was born. You're literally made of stardust, ancient matter recycled through cosmic processes, temporarily organised into a pattern that can think and feel and wonder. Every breath you take contains atoms that were once inside other people, scattered through the atmosphere and mixed by winds and time. With every breath you inhale atoms that were once breathed by Julius Caesar, by Buddha, by people whose names have been lost to history. The boundary between you and the rest of the universe is not as sharp as it seems. You're an eddy in the cosmic flow, a temporary pattern in the river of matter and energy. The Milky Way galaxy contains hundreds of billions of stars, and there are hundreds of billions of galaxies in the observable universe. But the observable universe is not the whole universe. It's just the part we can see, limited by the speed of light and the age of the universe. Beyond the cosmic horizon, space continues, perhaps infinitely, filled with galaxies we will never observe because the light from them hasn't had time to reach us yet. And remember, most of the universe is not what we see. The ordinary matter that makes up stars and planets and people, all the matter we can touch and observe directly, is only about 5% of the total. The rest is dark matter and dark energy. Substances we know exist because of their gravitational effects, but whose true nature remains mysterious. The universe is mostly made of things we don't understand. That should be humbling. Despite all our knowledge, despite all our progress, we still don't know what most of the universe is made of. Dark matter might be exotic particles that barely interact with ordinary matter. Dark energy might be a property of space itself, or it might be something else entirely. We have clues, hints, observations, but not yet a complete understanding. Yet this doesn't diminish the universe's beauty. If anything, the mystery enhances it. A completely understood universe might be less interesting than one that still holds secrets, that still invites exploration and discovery. And the universe is beautiful in its structure, in the way simple laws give rise to endless complexity. The laws of physics fit on a few pages, yet they generate galaxies and stars, planets and moons, oceans and mountains, storms and seasons, ecosystems and evolution. All the richness and diversity of existence. This emergence of complexity from simplicity is one of the universe's most remarkable features. Start with a few fundamental particles and forces, let them interact according to basic rules, give them time, and you get everything. The mathematics is simple, the outcomes are infinitely varied. The universe doesn't care whether we understand it. It existed before we asked any questions and will continue regardless of whether we find answers. But we can appreciate it nonetheless, can marvel at its scale and complexity, can take joy in our ability to comprehend even small parts of it. Perhaps that's enough. Perhaps we don't need to know why the universe exists to appreciate that it does, to find wonder in its workings, to feel grateful for the chance to be part of it, however briefly, however insignificantly. We've talked about the universe's origins and nature, but what about us? What about humanity's place in this vast cosmic story? Let's think gently about where we fit in, what our existence means in the context of 13.8 billion years of history. We appeared late in the story. If you compress the entire history of the universe into a single year, with the Big Bang happening at midnight on January 1st, the Milky Way forms in late February, the Sun and Earth in early September, the first simple life on Earth appears in late September, complex multicellular life in late November. Dinosaurs rule in late December, and all of human history, from the first stone tools to the present day, happens in the last few minutes before midnight on December 31st. We're newcomers, latecomers to a universe that had been unfolding for billions of years before we arrived. The universe doesn't need us. Life doesn't require us. The Earth managed perfectly well for billions of years without humans, yet here we are. Against all odds, in a universe that seems mostly hostile to life, on a planet that's mostly ocean and rock, we exist. We think. We feel. We wonder. We ask questions about where we came from and where we're going. Our existence required an extraordinary chain of events. The universe had to be just right, with the constants and laws fine-tuned to allow for stars and chemistry. Stars had to live and die, creating heavy elements and scattering them into space. A particular cloud of gas had to collapse into our solar system. Earth had to form at just the right distance from the Sun, with just the right size and composition. Life had to emerge from chemistry. Simple life had to evolve into complex life. Catastrophes had to happen at just the right times, clearing ecological niches for new forms of life. Primates had to evolve. The human lineage had to survive ice ages and droughts and predators. Your particular ancestors had to meet and reproduce, generation after generation for millions of years. Any of these could have gone differently. The universe might have had different constants and never formed stars. Our solar system might not have included Earth. Life might never have emerged, or might have remained simple. Dinosaurs might not have gone extinct, leaving no room for mammals to diversify. Humans might never have evolved. Your particular ancestors might have died young or never met. But it all happened. The universe exists with the right properties. Stars formed and died. Earth coalesced from stardust. Life emerged and evolved. And here you are, conscious matter contemplating its origins, asking questions that only conscious matter can ask. There's something profound about this. The universe, through us, has become aware of itself. For billions of years, matter existed without knowing it existed. Stars shone, galaxies swirled, processes unfolded according to natural law, but there was no one to see it, no one to wonder about it, no one to appreciate it. Then, on at least one small planet and possibly others scattered throughout the cosmos, matter organized itself into patterns that could think. Neurons formed networks, brains developed, consciousness emerged, and suddenly the universe had eyes to see itself, minds to understand itself, voices to ask questions about itself. This is extraordinary. You are the universe experiencing itself subjectively, Carl Sagan said. Every thought you think, every feeling you feel, every question you ask, These are all the universe's thoughts and feelings and questions, happening through the particular arrangement of matter that is you. This perspective doesn't diminish us, it elevates us. We're not just observers of the cosmos, we're participants in it. We're not separate from nature, we're nature, complex enough to study itself and sophisticated enough to wonder about its origins, and we're probably not alone in this. The universe is so vast, with so many planets orbiting so many stars in so many galaxies, that it seems unlikely we're the only conscious beings to ever exist. Somewhere out there, perhaps scattered across millions of worlds, other minds might be asking the same questions we ask, wondering about origins and meaning and purpose. We might never meet them. Space is too vast, distance is too great, timescales too long. Civilizations might rise and fall without ever contacting each other. Islands of consciousness separated by enormous gulfs of empty space and time. But knowing they might exist changes how we think about ourselves. We're part of a larger community, a community of thinking beings scattered throughout the cosmos, each one a unique perspective on the universe, each one valuable and precious. This should inspire both humility and confidence. Humility because we're not special or unique in any cosmic sense, just one instance of consciousness among possibly millions or billions. Confidence because we're part of something larger, representatives of the universe's capacity for self-awareness. What we do matters, not because the universe cares, but because we care. We can choose to increase understanding or remain ignorant. We can explore or stagnate. We can cherish our brief moment of existence or waste it. We can recognize our connection to the cosmos or imagine we're separate from it. The story of the universe is also our story. The Big Bang created the matter we're made of. Stars forged the atoms in our bodies. Evolution shaped our minds. History brought us to this moment. We're not observers of the cosmic story. We're characters in it, brief appearances in an epic that spans eons, but real and meaningful nonetheless. And perhaps that's the answer to the question of our place in the universe. We're the part of the universe that can ask questions, that can wonder, that can appreciate beauty and seek truth and contemplate mystery. We're temporary, fragile, insignificant on cosmic scales. But we're also remarkable, conscious, capable of understanding, and that's worth celebrating. As we move deeper into these final chapters, let's think about acceptance, about making peace with the universe as it is rather than as we might wish it to be, about finding contentment in a cosmos that might not answer all our questions. The universe is not obligated to make sense to us. It's not required to be comprehensible or comforting or designed for our convenience. It simply is what it is, operating according to its nature, indifferent to our desires and expectations. This indifference can seem cold at first. We're pattern-seeking creatures who crave meaning and purpose. We want the universe to care about us, to have created us intentionally, to have a place for us in some grand design. The idea that we might be cosmic accidents, byproducts of natural processes without deeper significance, can feel lonely and disheartening. But there's another way to look at it. The universe's indifference means we're free. We're not bound by cosmic purpose or divine plan. We can create our own meaning, choose our own values, decide for ourselves what matters. The universe doesn't tell us how to live. We get to figure that out ourselves, and despite its indifference, or perhaps because of it, the universe is extraordinarily generous. It gives us existence, consciousness, the capacity for joy and love and wonder. It provides a stable planetary home, at least for now. It offers endless beauty to observe, endless mysteries to explore, endless opportunities for discovery and growth. Think about what the universe provides freely. Every photon of sunlight that warms your skin, every atom of oxygen you breathe, every bit of water you drink, all of this comes from natural processes that operate whether we exist or not. The laws of physics allow for chemistry. Chemistry allows for life. Life allows for consciousness. None of this had to happen, but it did. Accepting the universe as it is means accepting both the wonder and the indifference, both the beauty and the randomness, both the order and the chaos. It means acknowledging that bad things happen without reason, that suffering exists without purpose, that the universe contains both creation and destruction, both birth and death, both joy and sorrow. The universe creates stars and then destroys them in supernovae. It brings life into being and then wipes it out in mass extinctions. It's neither good nor evil, neither kind nor cruel. It's simply natural, operating according to laws that don't include moral considerations. This can be hard to accept. When tragedy strikes, when we suffer, when we lose people we love, we want there to be a reason, a purpose, a meaning behind it. The idea that it might be random chance, just the natural operation of physical processes without deeper significance, seems insufficient, almost insulting. But acceptance doesn't mean we have to like it. It doesn't mean we can't grieve or feel angry or wish things were different. It just means we acknowledge reality as it is, rather than insisting it be something else. There's a kind of peace that comes with this acceptance. When we stop fighting against the way things are, when we stop demanding that the universe conform to our expectations, we can begin to appreciate what actually exists rather than mourning what doesn't. The Stoic philosophers in ancient Greece and Rome developed practices for cultivating this acceptance. They distinguished between things within our control and things outside it. We can control our own thoughts and actions, they said, but we cannot control external events, other people's behaviour, or the fundamental nature of reality. Peace comes from focusing on what we can control and accepting what we cannot. We cannot control whether the universe had a beginning or has always existed. We cannot change the laws of physics or the speed of light or the expansion rate of space. We cannot make the universe care about us or give us the answers we seek. These things are outside our control, but we can control how we respond to the universe we find ourselves in. We can choose curiosity over fear, wonder over despair, acceptance over resistance. We can appreciate the beauty and complexity around us. We can form connections with other conscious beings. We can pursue understanding even when complete knowledge eludes us. Accepting the universe as it is also means accepting ourselves as we are. We're part of nature, governed by the same laws made of the same matter. Our brains are biological organs shaped by evolution, limited in their capacities. We cannot think infinitely fast or hold unlimited information. We cannot perceive all wavelengths of light or all frequencies of sound. We're finite beings in an infinite cosmos. This should inspire compassion for ourselves and others. We're all doing our best with limited brains and incomplete information. We all make mistakes, fail to understand, struggle with complexity and uncertainty. That's part of being human, part of being finite creatures trying to comprehend something much larger than ourselves. So when we contemplate the question of what sparked the Big Bang, we can do so with gentle curiosity rather than desperate need. We can explore possibilities, consider theories, appreciate what we've learned, and accept that we might never have a complete answer. The not knowing is part of the human experience, part of what makes us seekers and wanderers. And in accepting what is, we might find something unexpected: gratitude. Gratitude for existing at all, for being conscious in a universe that's mostly unconscious. Gratitude for living in a time when we can ask these questions and have some hope of approaching answers. Gratitude for the beauty and complexity and mystery of it all. The universe is what it is, and what it is extraordinary. In these final moments together, let's think about time itself one more time, not as a problem to solve, but as something to experience. As we rest here in the eternal, now that's the only moment we ever truly inhabit. We've talked about time extending backward to the Big Bang and forward into an unknown future. We've considered whether time had a beginning or extends infinitely into the past. We've explored time as a dimension of space-time, as an emergent property, as something that might be fundamentally strange and counterintuitive. But there's another way to think about time, not as something to understand, but as something to be present within. Right now, in this moment, as you listen or read these words, you exist in the present. The past is memory. The future is anticipation. But the only moment that's actually real in your direct experience is now. This present moment contains everything you can actually know about existence. The Big Bang happened in the past, but you don't experience the past directly. You experience memories of the past, thoughts about the past, evidence of the past, but the past itself is gone. Similarly, the future hasn't happened yet. You can imagine it, plan for it, worry about it, but you cannot experience it. Only the present is available to direct experience. And in this present moment, the question of what sparked the Big Bang is just a thought, just words in your mind, just concepts floating in consciousness. The actual Big Bang, whatever it was, is not here in this moment. Only the question about it is here, only your contemplation of it. There's something liberating about recognizing this. All our questions about cosmic origins, all our theories and speculations, all our wondering about what came before and what happens after, all of this happens in the present moment. The mysteries we contemplate are real, but our contemplation of them is what we actually experience, and in the present moment, divorced from all our thinking about it. Reality simply is. You exist. Consciousness is happening. Experience is occurring. Whether the universe had a beginning or has always existed, whether it was sparked by quantum fluctuations or divine intention or something else entirely, none of that changes the fact of this present moment, the immediate reality of existence right now. Meditation practices in various traditions emphasize this presentness. They teach letting go of thoughts about past and future, releasing the constant mental chatter, and simply being aware of what is right now, your breathing, sensations in your body, sounds in the environment, the simple fact of being conscious and alive. This isn't to say that questions about the past and future don't matter. Of course they matter. Understanding history helps us navigate the present. Thinking about the future helps us make better choices. Wondering about cosmic origins enriches our lives and expands our perspective. But we can hold these questions lightly, without letting them disturb our peace, without becoming so lost in thinking about other times that we miss the only time we actually have, now. The universe exists now. Stars are shining now. Galaxies are swirling now. Space is expanding now. All the grand cosmic processes we've talked about are happening in this present moment, not in some abstract past or future, but right now, as you exist and experience, and you are part of those processes. You're not a separate observer watching the universe from outside. You're an integral part of the cosmic unfolding, consciousness emerging from matter, the universe experiencing itself in this present moment. When you breathe, you're participating in the carbon cycle, exhaling carbon dioxide that plants will use for photosynthesis, inhaling oxygen that photosynthesis produces. You're connected to the biosphere, to the web of life on Earth. When your heart beats, you're circulating blood made of atoms forged in stars, delivering oxygen to cells that metabolize nutrients and generate energy. You're a complex chemical process, maintained far from equilibrium by the flow of energy from the sun. When you think, neurons fire electrical signals, release neurotransmitters, form and strengthen connections. You're the most complex structure we know of in the universe, a pattern of matter so intricate that it can contemplate the origin of patterns itself. All of this is happening now, not in the past, though your atoms have a history stretching back to the Big Bang. Not in the future, though your existence will leave traces that persist after you're gone. Now, in this eternal present, that's the only moment you ever truly experience. And in this now, the question of what sparked the Big Bang becomes less urgent. It's still interesting, still worth exploring, still a valid subject of inquiry. But it's not something you need to answer to exist, to be conscious, to appreciate the wonder of being alive. The present moment is enough. It contains everything you can actually experience. The rest, the past and future, the distant galaxies and the deep origins, all of that exists as thoughts and concepts and questions in this moment. So as we approach the end of our journey together, as we prepare to close this exploration of cosmic mysteries, let yourself rest in this present moment. Feel your breathing, notice the sensations in your body, hear the sounds around you, be aware of being aware. The universe began somehow, sometime. It evolved and expanded and cooled. Stars formed and died. Planets coalesced. Life emerged. Consciousness arose. And here you are now, in this moment, briefly aware of the vast mystery of existence. That's enough. That's everything. The rest is just thinking about what is, and what is already perfect in its strange, mysterious, wonderful way. Thank you for staying with me on this long, gentle journey through one of existence's deepest mysteries. We've spent more than 2 hours together exploring the question of what sparked the Big Bang, if there was nothing, and I'm grateful you chose to spend this time contemplating these profound ideas. We've travelled from the first fraction of a second after the Big Bang, through cosmic inflation and quantum fluctuations, through theories of multiverses and bouncing universes and eternal inflation. We've thought about time and causation, about something and nothing, about the limits of knowledge and the beauty of mystery. We've explored what we know and what we don't, what we might discover and what might remain forever beyond our grasp. And now, as we reach the end of this exploration, let's return to our original question. What sparked the Big Bang, if there was nothing? The answer, as honestly as I can give it, is that we don't know for certain. We have theories, possibilities, ideas that might be true. Perhaps it was a quantum fluctuation in a pre-existing vacuum, allowed by the probabilistic nature of quantum mechanics, that inflated into our universe. Perhaps it was a bounce from a previous contracting phase, with time extending infinitely into the past. Perhaps time itself began with the Big Bang, making the question of what came before meaningless, like asking what's north of the North Pole. Or perhaps the answer is something we haven't thought of yet, something that future physics will reveal, surprising us the way quantum mechanics and relativity surprised earlier generations. The universe has a habit of being stranger than we imagine. But not knowing the complete answer doesn't diminish the wonder. If anything, the mystery makes it more beautiful. We're conscious beings asking questions about the origin of everything, using minds shaped by evolution to contemplate cosmic birth. That's extraordinary, regardless of whether we find the ultimate answer. If you enjoyed this slow drift through cosmic mysteries, a like and subscribe helps others find these calm explorations of profound questions. And if you have thoughts about what we've discussed, if this journey has sparked questions or ideas or feelings, the comments are a space for sharing. To those already part of this community, thank you for being here, for bringing your curiosity and wonder to these explorations. Wherever you are in the world right now, I hope you found some comfort in this journey. I hope your breathing has slowed, that the weight of the day has lifted from your shoulders, that your thoughts have quieted into a peaceful contemplation of mysteries that have no urgency, no deadline, no need for immediate answers. Look up at the stars, if you can see them from where you are, or imagine them if you can't. All those points of light, each one a sun perhaps with planets, perhaps with life, perhaps with conscious beings asking the same questions we ask. And between them, the vast darkness, space itself expanding, carrying galaxies away from each other, the universe growing older and larger with each passing moment. All those stars came from the Big Bang, emerged from that first moment of cosmic expansion, 13.8 billion years ago. The atoms in your body came from earlier generations of stars that lived and died before our sun was born. You're made of stardust, ancient matter recycled through cosmic processes, temporally organised into a pattern that can think and feel and wonder. The mystery of how it all began remains. Whether sparked by quantum fluctuations or eternal inflation, or divine creation, or something else entirely, the ultimate origin might always be beyond our reach. But here we are nonetheless, existing in a universe that permits existence, asking questions in a cosmos that enables consciousness, wondering about beginnings in a reality that includes us, however briefly, however improbably, and perhaps that's enough. Perhaps the fact of existence itself, the sheer astonishing improbability that there is something rather than nothing, that matter can organize into patterns that think, that the universe includes consciousness and beauty and meaning. Perhaps that's the real miracle, more wonderful than any answer we might find about how it started. Sleep well tonight. Dream of stars being born in the depths of nebulae, of galaxies swirling through the cosmic night, of the first light spreading through the early universe, illuminating a cosmos just beginning its long, strange journey, from simplicity to complexity, from uniform plasma to stars and planets, and eventually to you, lying here now, thinking about where it all came from. Good night. Rest in the mystery. There's no need to solve it tonight, or ever. Just know that you're part of something vast and ancient and ongoing, a cosmic story that includes you in this chapter, in this moment, in this brief and precious awareness. Dream peacefully. And when you wake, the questions will still be there, patient and profound, waiting to be explored again whenever curiosity calls you back to wonder. Good night.